Google's Big Table handles petabytes of data, serving billions of requests per second. The secret? LSM-Trees. But here's the thing. 90% of engineers struggle to explain the difference between BTrees and LSM-Trees, the fundamental data structures powering almost every database. By the end of this video, you'll know exactly how to choose the right one for your system and ace your next system design interview.
Now that we've set the stage, let's define our problem. We need to design a key value store that supports high read and write throughput. Functional requirements include the ability to insert, update, and delete keys, as well as retrieve values by key. Non-functional requirements are low latency for both reads and writes, high availability, and scalability to handle millions of keys. A clarifying question we should ask is, what is the read-to-write ratio? We'll assume a read-heavy workload with 10 reads for every write.
This sets us up for some back-of-the-envelope estimations. Let's assume we need to store 1 billion keys, with each key value pair being 1 kilobyte in size. That's 1 billion times 1 kilobyte equals 1 terabyte of storage. If we expect 10,000 write QPS and a 10-to-1 read ratio, that's 100,000 read QPS. For bandwidth, 100,000 reads per second times 1 kilobyte per read equals 100 megabytes per second of read bandwidth. These numbers will guide our design choices.
With the foundation in place, let's tackle the high-level design. We'll use a distributed architecture with separate read and write paths to optimize for our read-heavy workload. The write path will consist of clients sending requests to a load balancer, which distributes them to API servers. The API servers then write to a primary database and asynchronously replicate to replicas. The read path involves clients hitting the load balancer, then the API gateway, and finally a cache. On a cache miss, the read request goes to a read replica. We separate read and write paths because it allows us to scale reads independently of writes. We might be tempted to use a single database instance for both reads and writes, but that would quickly become a bottleneck.
Here's where it gets interesting. The core logic revolves around choosing the right data structure for our database. We have two main contenders, BTrees and LSM-Trees. Let's start with BTrees. A BTree is a self-balancing tree data structure that maintains sorted data and allows searches, sequential access, insertions, and deletions in logarithmic time. BTree operations involve traversing the tree to find the desired key or location for insertion. B+ trees are a variant optimized for databases, where all data resides in the leaf nodes, improving range query performance. Now consider LSM-Trees. An LSM-Tree, log-structured merge tree, is a data structure that stores data in sorted files called SS tables, sorted string tables. Writes are initially buffered in memory in a mem table, then periodically flushed to disk as SS tables. This makes writes very fast. The trade-off is that reads can be slower, as they may require checking multiple SS tables. Most candidates stop here, but the key insight is understanding the read-write amplification trade-offs.
Building on that architecture, the next bottleneck is understanding compaction strategies and Bloom filters. LSM-Trees suffer from write amplification, meaning a single write operation can result in multiple writes to disk due to compaction. Compaction strategies, such as leveled and tiered compaction, aim to reduce write amplification by merging SS tables. Read amplification also occurs because a read might need to check multiple SS tables. Bloom filters help mitigate read amplification. A Bloom filter is a probabilistic data structure that can quickly tell you if an element is times not times in a set. By using Bloom filters, we can avoid reading SS tables that don't contain the key we're looking for. Pause and think, what could go wrong with Bloom filters? They can have false positives, leading to unnecessary disk reads.
Having locked down the core logic, we need to address scaling and performance. Caching is crucial for our read-heavy workload. We'll use a cache-aside pattern with Redis, high availability. We'll use leader-follower replication for our database. If the leader fails, a follower is promoted. Sharding allows us to scale horizontally. We'll shard our database based on key range. Now, at this point, your interviewer will push back. Why not just use consistent hashing instead? Here's how you defend this. Consistent hashing is a good choice when you need to dynamically add or remove nodes. However, key range sharding is simpler to implement and manage for our use case. Remember those billions of requests we mentioned in the hook? Sharding is how we handle that volume.
That said, there's a hidden problem here: reliability. Fault tolerance is paramount. We'll use redundancy at every level. API servers are stateless, so we can easily spin up more behind the load balancer. For monitoring, we'll track key metrics like QPS, latency, and error rates. We'll set up alerts to notify us of any issues. For example, if latency exceeds 100 milliseconds, we'll trigger an alert. An experienced interviewer will probe: what happens when the cache goes down? Your answer should be: we fall back to the database, but latency spikes. That's why we use cache replication.
The next piece of the puzzle is summarizing the trade-offs. BTrees are great for read-heavy workloads with low write volume, while LSM-Trees excel at write-heavy workloads. The main bottleneck in our design is write amplification in the LSM-Tree. Next steps would be to explore different compaction strategies to further reduce write amplification. Database use cases for BTrees include traditional relational databases, while LSM-Trees are used in NoSQL databases like Cassandra and LevelDB. Ultimately, the choice between BTrees and LSM-Trees depends on your specific workload and performance requirements.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.